according to the industry group code.org, there will be an additional 1 million jobs in programming compared to the number of students that graduate with computer science degrees in the US. So to reiterate, there will be a shortfall within the next 5 years of 1 million programming jobs, which is a huge number. President's Council of Advisors on Science and Technology, the retention rate for programming or computer science degrees is the lowest of all STEM disciplines at 24%, just over 24%. That's a pretty abysmal retention rate. One of the reasons for the low retention rate is the fear of programming that many people have. So because it's so different from what they normally do, and because it's so abstract, a lot of people are really afraid to start on programming tasks. And even when they do, there's a paper that says that for the first course, for the first programming course that students take, the fear of programming they have actually goes up, because they're starting to grapple with something that's so new that it's very hard for them to overcome that fear, and it actually increases over the course of the first programming course. One of the reasons we feel that there is this fear is because programming is a really abstract concept. Students cannot really imagine what's happening when they write their code and when they try to execute that code, and what's actually happening, how does it run on the hardware. There's a lot of mystery to programming, and that mystery, that abstract nature of programming, is probably the reason why there is so much fear associated with programming. My students and I designed PLP, or the Progressive Learning Platform, which is an interactive computer architecture simulator, so that students could actually visualize what's going on in the simulated system. But there's also another aspect. So the software is one side of PLP. There's another aspect to PLP, which is the hardware. So we not only have open source visualization of what's happening inside, but there's also a board, a board that we have, where in the center of the board there is an FPGA chip, and in this chip we can actually download the hardware description of PLP. So we've designed a processor that is a one-to-one match with whatever we simulate, so that students can actually look at what's happening in the simulation, get comfortable with it, and then they can actually put their programs on the hardware and make that hardware do some fun stuff. So in the past, we've put this board on a robot, and we've had a robotics competition in which students went in, and they, in the process of programming the robot for the competition, which was the engagement aspect of it, they also learned a lot about how to interface our different devices. So sensors from the robots, for example, were interfaced with the PLP CPU. So interfacing embedded systems, understanding the architecture, understanding how a program actually works with these other devices, all of those things were captured.
Very exciting system, because it integrates so many different types of learning principles all into one system. In that, first of all, it actually applies a grounding principle extremely well, in that it allows students to see what they're doing actually in the real world. So they can see, as they're working with the PLP system, they know that it's actually working on this circuit board in the real world. And they can see how it transfers over. Also, it applies a multimedia principle well, in that it uses videos to give the learners multiple examples.
Programming is becoming a 21st century skill, and I think one of the main reasons a lot of folks who get into writing code don't keep up with it, because they don't understand the real value of what the code is doing behind the scenes. With PLP, you get the additional feedback of exactly what's happening. Where are the things executing? What does it look like to see your code turn into binary? What does it look like to manipulate memory? And I think these constructs that you use in your introductory programming courses, when they have a hardware representation, they become that much more clearer. And I think we will be able to make a significant progress towards improving early programming instruction to this audience, and also maybe attract a lot of them to come over to computer science.
So my experience with the PLP tool was in a second-year computer architecture course where we focused mostly on assembly language, and I found that the tool was incredibly helpful because you got to actually see how the code that you were writing affects the system on a hardware or processor level. Because in previous classes we are told how to write code, but we never know how the computer actually interprets it. So I believe that through the tool we were able to figure out how everything works and therefore write better, more efficient code.
My experience with the PLP tool was within a computer microarchitecture course. The course was designed to help software engineering students better visualize what is going on with the hardware.
My programming skills before coming here were pretty reasonable because I had already acquired a minor in computer science, so I had taken a number of courses that actually really helped me a lot more than when I did my electrical engineering based computer science course.
The PLP tool was especially helpful because it allowed us to visualize, to see what some of the concepts we were learning in other courses, what was actually happening on the hardware.
After using PLP for a while, that had the effect of when I used higher level languages again, I found that I was thinking more about how to optimize my code and which things would be slower on the hardware and how they might actually be performed on the hardware.
The PLP tool helped us better understand these concepts that we were learning in algorithm and data structures classes by letting us visualize it and see right there in the software what was going on so that we could write better programs, which was the objective all along. PLP tool was very helpful in this because it had the tools within it to show us what was going on in the hardware on a simulation level so that we could better understand these concepts.
The best things about PLP for students, particularly younger students, is it gives them the freedom to work wherever they want. So when I took the equivalent of CST 250, we actually used FPGAs, and so the only way to program was to actually go into the lab and use the lab's computers and the lab's logic boards. So I was really limited in my experience to during my class and during my lab. Versus PLP, I found that I could actually, if I was inspired to try something, I could go home and play with it on my own computer and try new things and go and be up and beyond the assignments.
A visualization of what the program does when it runs on the hardware. So people or students can actually see the interaction of the software, of their software, more importantly, not just some simulated software, but their software running on the underlying hardware. And that gives them a really good scaffolding for their concepts of how things are going to execute. So once they have an understanding of the underlying hardware, or at least the organization, not the details of how you design the hardware, but just how the hardware works and how a program interacts with that hardware, that gives them a basis to hang their concepts on. And that we expect will take away the fear they have of programming. There's a negative cycle of not really understanding how programs work and having a fear of programming and then not being engaged because of that fear. So that because their motivation goes away because they're not good at it. Instead of that negative cycle, we expect to see a really good positive cycle where they understand how their program is working, and that helps them to gain confidence. That confidence helps them to be more engaged, to be more motivated, and that makes them better programmers. So it's a positive spiral that hopefully will play a major role in the retention of students in computer science and software engineering type programs.
PLP already does a really good job of incorporating feedback. However, we're looking to ways of improving this feedback even more, in that we're making it more responsive, to give more just-in-time feedback as the student needs it, and also to add more formative feedback, allowing them to get more exhaustive feedback that actually gives them more detail as to why they're making the errors they are at the points they're making.
So one of the other significant areas where I think there is a huge need, and especially scope for applying PLP is how you include women into computer science. Women in general have been having the hardest trying to cope up with what computer science is and to make a case for a career in the future. And so we're seeing a lot of this attrition of women who start out in the middle school with an aptitude for math and science, who could be really good computer scientists and software engineers, but as they get closer to choosing a college degree, they kind of taper off because they don't really understand the value of a computer science education. So one of the reasons for that is that the AP computer science classes are so code heavy, with Java being the main mode of instruction. However, they don't try to do enough to attract women from a creative perspective. And I think what PLP provides, when in conjunction with an AP computer science class, is the ability to be creative and see the results of creation manifest itself in hardware. And so that integration, I think, will have a huge impact in trying to attract women into computer science.
The progressive learning platform is not just something that we have used in the classroom to improve student outcomes, but it's also something that we proposed to the National Science Foundation as a what's known as a RIGI project, a research initiation grant in engineering education. And we were funded in 2011, and since then we've published 5 papers, or 5 conference papers for PLP and 2 journal papers using PLP and the studies that we conducted of PLP's effectiveness in improving student outcomes. So it's been a very interesting research project. We've used very different methods to do the research collection compared to what I'd seen before. So coming from an engineering background, I've always looked at quantitative stuff, but we did a lot of qualitative studies. We did focus group interviews. We had students write a number of reflections. So for each lab or each phase of a lab, or each phase of a project, students wrote a reflection essay, and I had a co-principal investigator who was from the English department who did a linguistic analysis of these reflection essays. I also had a collaborator who did the open coding or qualitative analysis of the reflections, as well as the focus groups that she conducted in the class or at the end of each semester. So I learned a lot about new research methods and how to look at gauging improvement in student outcomes from not just a quantitative perspective, but also a qualitative perspective. We're writing a few more grants to further disseminate PLP now that we have some data to show that it's effective. We want to partner with a number of schools and go out and get some of the big grants where we can actually do a lot of dissemination. The open source nature of PLP helps out a lot. We have a web portal where people can gather and talk about PLP, have any questions. There's a mailing list, as there is with any open source project. So we're trying to build this online community, which can then serve to be like a base, a home base for PLP, where international universities, universities all across the world can actually tap into this space and post their questions or download even course content and things like that for the progressive learning platform and for teaching microprocessors and even programming.